Awesome. So thank you everyone for sticking around for this. It's been a very full day. So as you just mentioned, right, my name's Seth. I'm a committer on Apache Flink. And I'm going to talk to you today about Stateful Functions, which is a project being developed under the umbrella of the Apache Flink organization. If you're familiar with Flink, you likely know it as a world-class stream processor. It's very popular in the data space. And so that leads to an obvious question, right? What does a stream processor have to say about serverless? And what I hope to show you today is that the problems that stream processors like Apache Flink have been tackling for the past decade are the same sets of problems that are relevant to the serverless space today. So before we get into it, I want to do a little bit of table setting. I think these terms serverless, stateful serverless are a bit overused, right? They were just this past talk, for instance. And everyone's using them to mean slightly different things. So I'd like to give you my definition that I'm going to be referencing for the remainder of this session. Serverless to me is not a particular technology like Kubernetes or a particular product like AWS Lambda, though those all fall under the umbrella. But it's a realization of modern infrastructure capabilities, which allows us to iterate more quickly and with more confidence. So we're a business, we're running a web app, traffic spikes, that should be good news, right? It means that our business is doing well. But oh no, we need to requisition more hardware, install VMs, set up load balancers. Or at least we did. But today we can simply increase our replica counts. Or even better, we have a horizontal scaler that's going to manage that automatically. And so really what serverless means to me is it is a paradigm for solving a class of problem at the infrastructure level. And that's really important, but most of us are not building infrastructure as our core business objective. We're building applications. And so stateful serverless, in my mind, is about bringing these advances up to the application level where we're all working day to day, along with some key primitives that any real world application needs. So consistent durable states. Your application needs to be able to retain information that it can act on in the future. Cloud native fault tolerance. So as we're managing that state, we want to make this tenable. I'm not simply suggesting we throw a database on top of Kubernetes and call that cloud native or call that easy. But I want to look into what these modern infrastructures are really good at and see if we can't lean into their strengths to make our lives in production as easy as possible. And finally, we want simple messaging between these systems. So your business is not built on a monolithic service or monolithic function, right? But it's a collection of systems that need to communicate with each other in arbitrary and complex ways. We want to make that as simple as possible. So there shouldn't be any service discovery. I don't care where code is running. I don't care what language it's implemented in. I just want to invoke it. And we want strong ordering guarantees amongst these messages, because if service A sends 2 messages to service B, I want to ensure that they're both processed, they're processed in order, there's no duplicates, there's no drops. Consistency makes things easier to reason about, and easy to reason about code is more simply correct. So this diagram shows a very traditional 2-tiered application architecture, something I'm sure everyone here is very familiar with. Businesses deployed via stateless tier, which allows for simple deployments, dynamic rescaling of services, right, our good core serverless benefits. State is then managed on a separate tier via a database or other data store, right? The details are not so important. And when an application is going to receive a request or other message, it's going to communicate with that database, potentially updating some values, and then do one of 3 things. So one, it could do nothing. It could be that this message was simply to update a value in state, right? User moved and we modified their address. Number 2, we may send a result back to the caller. So we are shipping something to a user, and so we want to look up that address. So we read it out of state and we sent it back. Or number 3, we are going to invoke another service repeating this cycle. You can consider these different components invoking each other as a sort of data flow, which leads to the obvious question, what happens when something fails? Well, a fundamental problem with this architecture is that for any failure in any call across a service boundary, it becomes very hard to reason about which of the desired outcomes were actually achieved. Applications are forced to have a method of determining whether or not to attempt a retry or somehow make their state updates idempotent. But what if we inverted this problem so that messaging actually runs through the database? Well, it turns out this is exactly what stream processors like Apache Flink have been doing for years to provide what we call exactly once state semantics. Business logic is going to remain stateless and deployed as a separate service from data storage, so those core serverless benefits remain. But now messages are going to flow through the database, and we've inverted the caller. So the database is actually going to call into these stateless containers invoking our functions, supplying state as part of the payload of each message. These application functions return back both state updates and messages to be sent to other functions. And by moving messaging from the compute layer to the storage layer, state and messaging is easily made atomic. And so if something fails for whatever reason, the state update is always rolled back, so retries are always idempotent. And as you may have guessed where this was going, right? This is exactly the approach taken by Apache Flink Stateful Functions. So we're using a Flink cluster for message routing and state management, while allowing the actual functions containing application logic to be deployed in a separate compute tier. And this can be anywhere you like. So we could have functions deployed as standard Kubernetes services, KNative. We could use a wholly managed service like AWS Lambda. Maybe we have a function that's deployed on specialized hardware and it's not really serverless. We can do that too. You can deploy our compute anywhere we like. And what this gives us is a runtime where compute and state are logically co-located for consistency, but at the same time physically separated. All state accesses and updates are integrated as part of the function invocation request and response. And so if we look through our list of what we want in a proper stateful serverless architecture, simply by virtue of having our compute run as stateless entities, we very simply get these initial serverless benefits. We can scale things, we can easily upgrade and roll them back. But what about our stateful primitives, those extra bullet points we want to meet? Well, to talk about that, I want to talk about some of the core concepts when building a stateful functions application. You're going to be developing several services, or what we call functions, very creatively, that are basically small pieces of code or logic representing entities within an application. So you could, for example, define a function type representing a user with a single instance of that function type representing a single user in your application. These function instances are invocable through messages and do not consume resources while inactive, or simply while they're not actively being invoked. What this means is the runtime can host a theoretically infinite number of function instances within a fixed finite set of hardware resources. And this whole thing is polyglot from the ground up. So because compute is separate from everything else, it can be implemented in any language. There's a very simple protocol. This is not like a database driver. It's a protocol you can readily implement against directly. And that means we're going to support out of the box any language that can handle HTTP or gRPC, which is to say basically any language you're using in production. That said, just because you can implement directly against the protocol doesn't mean you necessarily want to. And so the community does ship a number of predefined SDKs that wrap that protocol in some higher level idiomatic constructs. And so there's Python, Java, Golang, Rust. There's even a Haskell SDK that recently popped up in the community. Hopefully your favorite language coming soon. Additional SDKs is very high on our prioritization list. So compute's fine, compute's interesting. Lots of people can write code and we can have these little stateless functions. But where things get interesting is that we can invoke these functions with dynamic messaging and consistent state. So if you have used Apache Flink in the past, maybe the data stream API or the SQL API, and you're familiar with it from a data engineering perspective, you may be thinking Dataflow DAG. And that is not the case. So functions are able to message each other dynamically, and they can do so in arbitrary, complex, round-trip, round-robin ways. So any function can message any other at any time. All a function needs to know to invoke another is the type of function it wants to invoke and the ID of that particular instance. So if I want to talk to a user, I'm going to talk to the user function type and supply the ID. So talk to user 1. There's no service discovery here. The runtime is going to ensure that all messages are routed to the correct location. So I don't have to be concerned with where user one is physically running or even what language that function was implemented in. I just fire and forget that message. We're going to provide the consistency and guarantees out of the box. And all of this can be done with what we call exactly once state semantics. So these function instances can maintain local states, while the runtime will ensure that messaging and state updates are integrated so that you can have an out-of-the-box efficient consistency across event inputs to the application state itself, and outputs delivered from the application. And this whole thing is no database required, or better put, we are using our Apache Flink cluster as our database. So Flink has long provided large-scale consistent state management through concepts of state backends and distributed snapshotting. I'm not going to go into the full details of how that works in this talk today. But what's important is that Flink clusters are able to store state locally within clusters for fast accessing. And that state is then going to be periodically backed up to simple blob storage. So in the case of failure, let's say a pod or some task manager in your Flink cluster goes down for whatever reason, there's hardware failure, there's a blip in the network, anything may happen. When that entity restarts, it is simply going to download its state from blob storage and continue processing on. So we are not reliant on stateful sets or persistent volumes for high availability of state. Even the component that is actually managing state in our application can be ephemeral. In using this model, organizations have scaled to managing hundreds of terabytes of state within Flink clusters themselves, with the confidence they're delivering consistent, reliable results. So we can really scale this thing up, but we can also manage really small scale. People have also deployed Flink on Raspberry Pis. So wherever your organization is, however much data it needs to manage, we readily support that. Okay, so I said this was hands-on. That was enough concepts. Let's look at some code. I want to start by doing something a little simpler just to make sure that we're all wrapping our head around the basic idea and see what the SDK looks like, and then take a peek at a more real-world example. And so like any good introduction to a new bit of software, we're going to start with Hello World, but with a StateFun twist. And I want to make a greeter, something that's going to say hi to our users, but we're going to do so statefully. Our greeter is going to receive messages from users, and it is going to respond with a customized greeting for that particular user based on how many times that user has been seen so far. So if I send it a message, it'll say, hello, Seth, welcome back, Seth, third time's the charm, Seth, managing that state, managing that count. But it's going to manage the count for every individual user independently. So if someone else wanted to message it, let's say John wanted to send a message, it would say, hello, John, welcome back, John, third time's the charm, John. And that's all happening consistently, durably, and independently of my count. So as I said, our functions can be implemented in any language we like. And so we can have applications that are made up of many functions, each of which may be implemented in a different programming language. And so we need a common way of communication. We need a common type system. And so for that, we've decided to standardize on protocol buffers. It's a fairly robust serialization format, comes out of Google. I suspect a lot of people at this conference are familiar with protobuf on some level. And in particular, we have decided that all messages sent to and from functions are required to uniformly be protobuf any, which is the sort of super type of protobuf. And so when a message is sent around, it'll contain both the serialized bytes of its payload along with a URL describing the type. And so our receiving functions are able to quote unquote unpack that any message into some concrete type using its language specific protobuf library. Same thing is going to go for state. So it must be stored as protobuf any. You're writing your user code in any language you like, but the Flink runtime is a JVM application. And so by doing this, Flink runtime only ever sees any. And it's just going to store those bytes and make it consistent and durable. That said, if this sounds a little boilerplatey, it could be if you were developing directly against the protocol. That said, all the language-specific SDKs offer those high-level constructs, and they mostly offer ways of developing exclusively against concrete types, so that any becomes an implementation detail and you only have to write well-typed code. Okay, so with all of that in mind, this is our basic greeter. It's receiving these greet requests. It's going to calculate a greeting, and then it's going to send the message to another function that will send our greeting as an email. So send it back to the user. So you could imagine that for every user in this application, there always exists an instance of this greet function. Think of it kind of like a class in object-oriented terms, right? It's the sort of function we're interested in. And we're going to have an instance for every individual user. So when I'm inside my function, I don't have to think about multiplexing against different users or whose state I'm looking at. I'm always scoped in a very particular, what we call address, made up of a function type, the sort of function, and an ID, the particular function. And so in this case, my ID is likely to be my user's unique UID. We get two parameters into our function. We have a context that gives us some runtime capabilities, we'll see in a moment, along with the actual message sent to us. As you can see here, we're using Python 3 type annotations. So while yes, it is true that the message is flowing through the runtime as protobuf any, it is going to be automatically unpacked for us, and I only ever have to work against this specific type. Pack and send is going to take our computed greeting, we'll see how we did that in a moment, and wrap it in an any type, hide all that boilerplate from us, and shoot it off to our email sender function, a different function type. In particular, when we send a message to a function, we always specify the function type. So what sort of function do you want to send this message to? And an ID, which particular instance. In this case, my function type is demo/email sender. It is a logical type. I'm not specifying what language this code is written in, how it was implemented, where it's running. Just this is the sort of function I want to message. And my ID, which in this case is the email we are sending the message to. So you could think that this email sender function represents a sort of virtual inbox that we can message. Okay, so then I think the most powerful aspect of stateful functions going into our create personalized greeting method is that they can have, well, durable states, right? This is kind of the value proposition we're offering. And so this is a snippet of what this function may be doing. It's very simple code. All we're doing is keeping track of how many times we've seen a particular user and then using that number to create a special greeting based on that count. So state is access and updates through this invocation context. And so I'm saying, get me my scene count. I'm using pack and unpack as some helpers to go from protobuf any to my specific scene count type. And otherwise, that's it, right? This is just plain old Python code. Instead of having my count as an instance variable, I am accessing it through the context. But otherwise, I just write plain old simple CS 101 code. Consistency, durability, fault tolerance, that is all given to me for free as primitives by the stateful functions runtime. And so that's it. That's all you need to do to implement a function. The last step is to expose that function to the runtime so it may be physically invoked. And so we can expose our functions via HTTP or gRPC, as I said above. First thing we're going to do is bind our physical Python code to that logical type. So you can see I have what I'm going to call my function registry that does this binding. And in this file, I have implemented two functions. I have my greet and I have my send email. And this is where kind of rubber meets the road. And when I say send a message to my email sender, this is how the runtime knows which physical function to invoke. The fact both of these functions are implemented in Python and they're both implemented in the same physical file, but that's really just so I could fit it all on one slide. Email sender could have been written in Haskell and running halfway around the world. All our functions can be implemented separately and deployed independently of each other. So we'll bind them to the runtime. And then each SDK is going to ship with some sort of request reply handler. And this is the thing that actually runs our, understands our low-level protocol. And so in this case, it's going to take an HTTP payload, deserialize it, invoke the correct function, accumulate its side effects, what state needs to be updated, what messages need to be sent to other functions, and then re-encode that in our response protocol and send it back to the Flink cluster. Last thing is to actually expose it via an HTTP endpoint. In this case, I am using Flask, but that was just because I like Flask. You can use anything you like. So any way you can expose this to the network. You could have it as an async IO. You could have it as an AWS Lambda function. So maybe I don't want to do any management of my code. I could have it run as a pure AWS Lambda function. That's it, right? So that is the basics of a stateful functions application. And Hello World is great. Hello World is nice to learn some basic concepts, but your business is not built on sending customized greetings to users. At least I highly doubt that. But it may be built on model serving. And so this is the real world application I want to take a look at. We're going to build a stateful functions application, or we're going to take a look at one that does fraud detection over credit card transactions in real time. So a transaction comes in, it is going to pull together a feature vector made up of different bits of information. So we're going to look and see how many times has this account reported fraud in the past 30 days. We're going to look up a trustworthiness score of our merchant, potentially lots of other bits of information that are being stored in states. We're going to coalesce all that together into our feature vector, invoke some model that is likely provided to us by a data science team. We're going to score that and then take an action based on that score. So if it's above some threshold, we'll send an alert to the user saying, hey, I think something went wrong. So let's take a look at that. I'm going to go ahead and share this. So this is the fraud detection application. As I was saying, we're looking at a fraud model serving demo where we are doing fraud detection of a credit card transaction. I have implemented all of these functions in Python, and I've implemented them inside of a single executable, but that is just for simplicity of the demo. Each function could be implemented in its own language, deployed completely separately from each other. That is not a hard requirement. And so we're not going to look at all of it, but I want to just take a look at two of the functions. The first is our fraud count. And so for each account, we are managing, keeping track of the number of confirmed fraudulent activities against that account over the past 30 days. We can take in 3 message types. So there is confirm fraud, which says, hey, I confirm that this really was not me, someone else was fraudulent against me. Query fraud, so someone is asking how many times have we seen fraud for a particular account over the past 30 days. And expire fraud, so once some activity is more than 30 days old, we want to decrement our count. If we look at this, again, what I really just want to show off is that it is very simple code. So if a confirmation comes in, we're going to read out our states, which is the reported fraud. We are going to initialize it if it hasn't been set before, or increment that value, and then set it again. Other than the fact that we have taken our variables and we are managing them through the context, we are writing really simple, just CS 101 code. Some other features that are kind of interesting. We can send messages to any other function, but we can also send a message to ourselves. So I'm sending a message to myself, but with a 30-day delay. And so this expiration message will be made fault tolerant by the system. Even if things go down for whatever reason, this message is guaranteed to arrive. And so it'll arrive back in 30 days. And when it does, that is our cue to ourselves that, hey, we should go ahead and decrement this value. So it's a rolling 30-day count. If it's back to 0, we'll delete it entirely. Otherwise, we'll just decrement and store the updated value. And when a query comes in, when we're building up a feature vector to that needs this fraud count, we're going to simply read out the value, have a default if there's nothing set, or otherwise just reply back to the caller. And so there are a number of other functions here, but maybe the most important is the transaction manager. So this is the one that is going to get in credit card transactions and build up feature vectors, score it against the model, and take some action. When a transaction comes in, we'll cache it into state. We want to make sure that it sticks around. We are going to then send messages to these other functions. So we are going to query our fraud from our fraud counter based on that logical type for this particular ID. We're also going to get some merchant information and some other account information. When these messages come back, when our functions reply back to us, we're going to have our feature vector and we will message our model. And so we'll say, hey, our model for this particular account, because maybe we have different configurations for each particular account or different thresholds that we are going to consider fraudulent. Hey, here's the feature vector. Do what you need to do. And when that finally comes back to us, we are going to say, is it above some predefined threshold? Do we consider this fraudulent? If so, I'm going to write something out to a Kafka topic. And of course, clear my state because I want to be a good citizen and not store data longer than I need to. Each of these functions are being bound to my function registry via these logical names. And finally, we expose it, in this case via Flask, but what Python web framework of your choosing. So let me go ahead and share one last thing. So if I go over here, I have this up and running. This is the Flink UI. If you're not familiar, it shows us the running Flink cluster that is managing all of this for us. There's not a ton to see here other than it's up and we've processed, I don't know, 17,000 messages. I'm running this at parallelism 1, so my Flink cluster is very small. It's only actually running on a single core because I know I'm not managing a lot of state. And my compute is running separately. So, hey, I don't need a lot of CPU in the Flink cluster itself. We have what are called checkpoints running in the background. So it's fault tolerant. If this goes down for whatever reason, hey, it is going to re-download its state off of, in this case, S3 and continue processing on as if nothing ever occurred. And finally, we can take a look at what is actually running. I have the Flink cluster with it, one task manager and one job manager, the minimum amount I need to be going, along with my Python worker that has this code. And because it is all stateless, if I go into my charts, these are just plain old Kubernetes deployments. Hey, maybe I want to scale up. Maybe I would put a horizontal scaler on this in a real world scenario, but I want to change my replica count to 10. Well, I can just go ahead and do that. And so Q control apply -F, StateFun functions. It is going to make that change for us because our user code is stateless entities. These are going to, we're going to be able to do this without any downtime. We're not going to lose any consistency or durability. We're going to get correct, reliable results. And so if I go back and check my pods, you will see, hopefully in a moment, that a large number of pods are going to come up and begin to run. I don't particularly feel like waiting at the moment, but I think everyone gets the basic idea. So thank you all for sticking with us. It's kind of a crazy talk, but yeah, that is the basic idea with the Stateful Functions. So we are really being the database for your serverless infrastructure, providing consistent messaging and state across a whole host of entities, allowing complex, consistent communication and results. If you are interested in learning more, you can go to statefun.io or on Twitter, statefun_io, or reach out to the Apache Flink community. Thank you so much for coming with me across multiple Zoom rooms. And if there are any questions, I'd love to take those now.